So I'm going to attempt to give you some insight into the formulas that you need to know for midterm number 2. Starting in chapter 25, the first formula that you'll need to be able to use is the voltage due to a continuous charge distribution. So you use this when you are calculating the voltage due to a rod, a ring, or a disc. So it's when the charges are distributed over a continuous charge distribution. The next formula is for the potential energy of a system of charges. So the formula sheet gives you the potential energy for any two charges, Q1 and Q2, separated by a distance 1, 2. So if you have multiple charges in some system, you would sum over all possible pairs. And I've showed you a video of that in the videos for this midterm. The next equation from chapter 25 you need to know how to use is calculating the electric field given the voltage. So voltage and electric field are related in a similar way that velocity and acceleration are. However, there's a difference here in that voltage is a scalar, electric field is a vector. So if you're wanting to calculate the entire vector for the electric field, it's the gradient of the voltage, which is the vector operator that gives you 3 components for that electric field. So you take the derivative with respect to x, with respect to y, and with respect to z to get your electric field vector. So that's it for chapter 25. For chapter 26, which is all about capacitance, there's just the basic definition of capacitance, which is the charge divided by the voltage on any capacitor. If you're calculating the potential energy stored in a capacitor, you have the choice of 3 formula. It's half QV, or if you don't want the Q, it's half CV squared, and if you don't want the V, it's 1/2 Q squared over C. So those are the formula that you use in the problems where you have capacitors and the plates are being pulled apart, or you have capacitors that are being connected to each other, or you have capacitors where dielectrics are being put in or out. Now, as far as dielectrics go, capacitance changes by a factor proportional to the dielectric constant kappa. So for a parallel plate capacitor, if you slip a dielectric between the plates, capacitance goes up. Kappa is always greater than 1. The formula for a parallel plate capacitor is epsilon naught A over D. A is the area of the plates, D is the separation of the plates. Okay, for chapter 27, which is current and resistance, you have the basic definition of current, which is the derivative of charge with respect to time. So current is defined to be the amount of charge passing any given point in any unit of time. What's going on in a wire as current flows is that the charge carriers, the electrons, although they're moving at high velocities, they're drifting in the direction opposite to the current, with a drift velocity equal to the current over the number of charge carriers per volume times the charge on the charge carrier times the cross-sectional area of the wire. Ohm's law is here that you're going to need, B's IR, I think everybody knows that one. And then resistance, R is rho L over A. There are a couple of problems that I did videos for using this equation. The most interesting ones are when the resistivity rho is not uniform, so you have to integrate rho as a function of x dx, or if the cross-sectional area changes as you move from one end of the conductor to the other, and that would be the wedge problem or the right circular cone problem. The wedge problem's in your notes, the cone I made a video for. If you need to calculate electrical power, you have 3 choices. You can use voltage times current, or you can use I squared R, or you can use V squared over R. Now both resistance and resistivity change with temperature. So resistivity at the hot temperature would be resistivity at the cold temperature times 1 plus the temperature coefficient of resistivity times the difference in temperature, T hot minus T cold. Now, assuming that the length and cross-sectional area don't change as the temperature changes, it means that resistance also has the same relationship as resistivity as temperature goes up or down. Okay, chapter 28 was just a Kirchhoff problem, so there are no equations for that. Chapter 29, now we're into magnetic fields. The force on a charge moving in a magnetic field depends on the cross product between the velocity of the charge and the magnetic field vector. And Q is the charge. So this force will always be perpendicular to both the velocity and magnetic field, and it will cause particles to go in circles. So circular motion is F net is mv squared over r. That's just Newton's second law for uniform circular motion. And if you equate qvb with mv squared over r, you get the formula for the radius of circular motion in a magnetic field. Now the thing you have to remember about using this formula is that this velocity is actually v perpendicular. And it has to be the velocity component that is perpendicular to the magnetic field. That is what makes it go in a circle. Any velocity component parallel to the magnetic field simply doesn't change when the particle enters the magnetic field. So if you're doing helical motion problems, you'll need this equation for the circular part and just the regular equation, velocity equals distance over time for the parallel parts. The next formula you're going to need for this midterm is Bill, or Li cross B. This is for a current carrying wire that's in a magnetic field. It feels force. This equation is used for the levitation problems, where wires are levitated against a gravitational field, or for problems where you simply have some geometric configuration of a wire in a magnetic field and you need to cross the segment of the wire with the magnetic field. Also in this chapter is the potential energy associated with a magnetic moment. So that's like a compass needle, where the magnetic moment is I times A. I is the current in the little current loop. A is the area vector of the loop. Remember, and it's perpendicular to the plane of the loop. Also, the torque on a current loop in a magnetic field is mu cross B. N is the number of turns of wire in the loop. U is the magnetic moment of the loop and the magnetic field. And that's, of course, what makes current loops rotate in magnetic fields. I think that's pretty well it.